So basically, I'll give this to you as an exercise, and you must have done it anyhow. You know that when you integrate of delta of some function of x around in some interval, which includes hx equals 0. Just one isolated 0. In other words, you're looking at function of h of x. It goes through 0. Here, this is h of x. And then Dirac delta function is supposed to give you a contribution because its argument is 0. So it's supposed to give you 1. But to give you 1, the definition of Dirac delta function is delta x. Delta of x equals 1 if you go from minus epsilon to plus epsilon, if you bracket the 0, as long as you do it in an open way. But because it's a function of h, you first have to do a transformation. And that transformation will just pick up a derivative because you'll define y equals h of x. Then dy will be dh dx. And that'll give you a derivative where the ends of the interval change because you've changed the coordinates, but as long as 0 is included there, this will happen, and you'll just pick up the value of the slope at 0 in this case. So that's where the Jacobian comes from. It just comes from this change of coordinates. And in d dimension, it becomes a determinant of Jacobian. It has to be a number. It has to be volume. So here we are. Now we have an operator. Various letters show up. I use curly L. And here, what we are saying is, and it's not obvious that things should work out this way. This is a linear operator, just like Green's function is a linear operator, because it's linear operator on space of functions, which are the densities. And what it does is, it takes a density, does something to it, rearranges it, according to the law of motion, and produces a density. Now, what we are assuming when we define this operator is that our laws are perfect. Our measurements are imperfect, but a higher being has promulgated a law that's absolutely perfect, and therefore law is described as a delta function. Any initial condition is unique to any precision whatsoever, unique result. And this could have been criminal, because now what we're saying is we are imperfect because we can't prepare the conditions very well. But the law is perfect. So our imperfection gets mapped into another imperfection. And it's not obvious a priori it would work. The way the theory is really buttressed, but we won't be able to cover it in this course, is that you study deterministic dynamics as a limit of noisy dynamics, where this kernel is a little Gaussian, saying I can predict something to a certain width. And then you show that in the limit of this width going to infinity, your predictions agree with these predictions. Now, on a fundamental level, this is guaranteed by this existence of natural measure. that you can define self-defined natural measure next. From now on, we work with this perfect law, and this is expression of what dynamics does on densities of trajectories. And it looks like nothing, right? But it'll give us everything from now on.